So now let's look at the compressor isentropic efficiency again. And here is the isentropic compression 1 to 2s, and here is the real compression 1 to 2. So in other books they actually make the isentropic process solid, and they make the actual one a dotted, because they say, well, any irreversible process we don't really know exactly what is the path. We know to start with 1, we finish at 2, but we don't know exactly its path. But in our textbook he ended up doing it in reverse. Anyway, so 1, 2s, and here is 2. And so this come from the definition of eta compressor, the isentropic efficiency. So what, the smaller one over the big one, the work ideal over the work actual. This should be T2s minus T1, and this should be T2 minus T1. And then he divide everything over T1, so that's why you see the T1 disappear, and this become T2 over T1, and this become T2s minus T divided by T1. And what happened to T2s over T1? He replaced it by the pressure ratio K minus 1 divided by K. So from this, and using the fact that the work compressor is H1 minus H2, this way it will end up being negative, that's okay, right? H1 minus H2, H1 minus H2, which becomes CB T1 minus T2. He will use this T2 over T1 from here. See what he did here? He took T1 out, so this become 1 minus T2 over T1, and he will replace T2 over T1 from this expression, and he end up with this. So that expression is very useful if you have the textbook in the exam or the quiz, and he just asked for the how much work of the compressor, and he give you T1 and the pressure ratio. You can just go ahead and use that expression immediately, P2 over P1 and T1. So this, in that expression, he did get the isentropic temperature T2s, and then he get the ideal work, and then he used the eta in order to come up with T2 minus T1, and so eventually he end up getting the work compressor. So all this is basically embedded in that formula. All those steps are embedded in that formula, so you can go ahead and use it. Alright, and if you also would like to get T2, personally you want to get T2 because you're going to use it later for the combustion chamber, you can use that expression, which is nothing but, bringing T2 here in terms of this T1. That is what this thing is. Okay, last year I think I made it a homework for them to starting from here prove this, but it's pretty simple. It's all just algebraic manipulation. You just bring this here and multiply by T1, you'll end up with that expression. It's nothing really. Right? So we will see an example now. So air enter the compressor. Here is the pressure P1, 100 kilopascal, and the temperature is 300 Kelvin, and the compressor pressure ratio is 8, that's P2 over P1, and the isentropic efficiency is 0.87. Find the exit temperature T2 and the pressure of the air leaving the compressor. Of course, the pressure, what would be the pressure? He said pressure ratio of 8. So if he start with 100 kilopascal multiply by 8, you get 800 kilopascal. You see that over here? So this is just using the pressure ratio. Now for the exit temperature T2, he is using that big expression over here. I'm personally not really a fan of using expressions that we don't really know where they come from, and I rather work from first principle. So I will get T2s, and then I would use the eta compressor to come up with T2. But in this scenario, in this case, we actually know where this expression come from, and we know it's applicable, so you go ahead and use it. Don't worry about it, right? Because it's really correct, right? So this will give you T2. The work per unit mass added to the air of the compressor, CB T1 minus T2, and you can do this, or I mean, if he didn't really ask for the temperature, we can just use this, right? Because we know the T1 300 Kelvin and we know the pressure ratio is 8. So we can use that expression for the compressor work. This is joule per kilogram. This is specific work. Right? Very good. And the work isentropic, it will just be the eta compressor multiplied by the work actual. Okay? Very good. So same thing happen also at the turbine. Starting from the heat, basically starting from what the definition of isentropic efficiency of a turbine. Here's a turbine coming from 3 to 4s. He did the same mistake again. Again, I would use this as a solid line and I will dot the actual thing. Anyway, he go from 3 to 4s and here is 3 going to 4, and that 3 and 4s are related to each other by this expression. Why? Because they are isentropic, right? 4s over 3. And the eta is the small work over the big work. In this case it would be the ideal work over, the actual work, that's the smaller one, and the ideal work, that's the bigger one. And so this should have been T3 minus T4, and this one should have been T3s minus what did I say? T3 minus T4 and T3 minus T4s, right? T3 minus T4s. And then he divide everything over T3. He divide this over T3, so that T3 here become 1 and this become T4 over T3. This was T3, right? And this is T4s. So you divide everything over T3, you get 1 minus T4s over T3. And what is T4s over T3? The pressure ratio. Okay? And the work is CB T3 minus T4. He took this T3 out, it become T4 over T3, and he bring this from over here, T4 over T3, and you end up with that expression. Exactly like the compressor, except that the relation is a little bit inverted, right? But if he, and we will see an example, if he asks for what's the actual work, and he give you the inlet temperature to the turbine, T3, and the pressure ratio, you can just go ahead and use that expression directly, right? And here is, in case you wanted T4, the exit temperature that is gonna go outside the turbine. So here is the example, and exactly like the compressor. So you can read this. It's exactly the same thing. You want the exit temperature, he will use this. He want the work turbine. He said T3 minus T4 because he got 3 and 4, but if only he asked for this without the temperature, you could have used the expression for the turbine work. This guy. Knowing the isentropic efficiency, the inlet temperature, and the pressure ratio. Right? Very good. So now let's talk a little bit about the combustion chamber. So that combustion chamber require Q added, right? Here's a combustion chamber. The stuff come here, enter at T2 and leave at T3, and you need to put Q added. So this Q added is actually added in terms of fuel that they atomize, and those fuel droplets basically combust, and that combustion generate the heat. So we know that if you have 1 kilogram of fuel, you will generate this many joule by combusting it correctly. If you have complete combustion, you should liberate all the energy stored in that fuel. So that energy is called the heating value of the fuel. Okay, and it's in joule per kilogram. Alright? So if you know the kilogram per second of the fuel, and you know the joule per kilogram, then you got yourself the joule per second that is being added to the flow stream. Okay, so this Q added is doing what? Is heating the flow. So from the first law of thermodynamics, it should be m dot air, and it is Cp T3 minus T4. Right? What I'm doing here, I'm doing basically m dot air multiply by Cp, or multiply by H3 minus H4. Right? No, wrong. Something is wrong with this equation. Tell me, what is wrong with this equation? I'll give you a hint. So how much fuel we are adding here? M dot fuel. How much air is coming here? M dot air. How much is leaving? M dot air. Is it? Really? So we come up with m dot air, and we add fuel, and we still leave with m dot air. That's why you are saying it's m dot air H3 minus H4. Is that correct? So it's not correct, right? What should be leaving here? It should be m dot air plus m dot air plus m dot fuel. That what should be leaving. And how much is the m dot fuel compared to m dot air? 2%. So by saying m dot air Cb T3 minus T4, you are doing a 2% error, right? But you will see that a lot of people use this assumption. Of course, m dot air plus m dot fuel is more accurate, right? Definitely, it's more accurate. What else is wrong for a free quiz? What else is wrong in this equation? Q added m dot fuel multiplied by the heating value equal to m dot air Cb T3 minus T4. Yes, Cp. Which Cp? Is it Cb2, that was all air, the 1004, or the Cp of the combustion product? So this is correct. H3 minus H4, and you calculate H3 and H4 based on the local Cp. So if you are at station 3, what did I say? 3 minus 4. Sorry guys, it's 3 minus 2. Ouch. Of course, I bet you're all saying that what's wrong from the start, right? 3 minus 2. 3 minus 2. So what is wrong is that we said that H3 is CBT3 and H2 is CBT2. So no, this CB is completely different from that CP. But again, for a first order approximation, you will see people just using one CB that fits all basically, and say it's not, we are not going to use the CB air, we are not going to use the CB gas exhaust, we'll just use CB in the middle, and that should take care of things, right? So there are several level of sophistication that we will see. So here is a zero order approximation, kind of. So m dot fuel multiplied by the heating value is m dot air, a CP, a constant value for all the combustor from the start till the end, and T3 minus T2, right? And this is Q added, this is Q added, right? Both of them. This is from the fuel point of view, this is from the air point of view. And you can immediately realize then, if I just get m dot fuel over m dot air, you will see how m dot fuel over m dot air is Cp T3 minus T2 over the heating value. And if in the problem, if you ask about what is air to fuel or fuel to air mass ratio, or he simply will say fuel to air ratio, it's this equation. And that's why this is, by using this equation, you realize why the ratio is 2%, because the heating value is like really high. So for natural gas, that number is like around 30 megajoule per kilogram. 30 megajoule per kilogram. And what's Cp over here of the air? It's not in the megajoule, it's like 1 kilojoule per kilogram. So 30 megajoule per kilogram, 1 kilojoule per kilogram, right? 1 point something. And so that temperature ratio is what, or that temperature difference is what? He start with I don't know, 500 or 400 or something, and he finished at 1500, so you're talking about 1000. But still, this is megajoule, right? So that's why. So here is a typical heating value for different fuel. So liquid fuel is of the order of 40, 40 megajoule per kilogram. This is the heating value of jet A. This is a fuel that the military airplane would use, right? Natural gas, so it's not really 46, but I guess depending on the kind of natural gas, it depends from one place to the other, but I would say it's around 30 actually, right? So here is a very simple example. He said a combustion turbine utilizing natural gas as a fuel has a combustor exit temperature of 15K, that's T3, compressor exit temperature of 690K, that is T2. Estimate the fuel air ratio. So you run to the equation, and he got T3 and T2 natural gas. Let's use his table for now, and he got 46 megajoule per kilogram, and that CP is a value that he used as a constant for the whole combustor, and you can see how the ratio is like 2%. Okay, so this, and over here he's pointing out that if we wanna calculate the thermal efficiency, and again it's work net over Q added, and work net is the work compressor, it will end up being negative from here, plus the work turbine, or basically work turbine minus the absolute value of work compressor, and in that case you will make it T2 minus T1 divided by the Q added. Look at the CP, CP prime, CP double prime. So what he's saying is that let's use a CP for the air in the compressor different from the combustion chamber CP, different from the CP inside the turbine. Okay, and so you will get those values from a table in the textbook here, and that would be much better than just have you use one CP throughout the calculation. Right? What is the inverse of the thermal efficiency? The heat rate. Remember, the heat rate is just the inverse of eta thermal, but they really love to have the heat rate in BTU per kilowatt hour, and we said in order to do this we just need to use what, 3140 over eta thermal, right? So here 3412, and then it become BTU per kilowatt hour. He's also saying that for the plant, it's not just the plant is not just the turbine, the plant also has the generator. So if you want to calculate the heat rate for the whole plant, you better use not just eta thermal but multiply it also by the generator efficiency, which usually is pretty high. So I guess they are doing a better job in electrical engineering, I guess. I mean, look at the generator efficiency 98, and thermal efficiency 31%. So we look really bad for electrical engineering. Right, but we are stuck with the Carnot cycle basically as our lower limit, right? So he's giving us the thermal efficiency and the eta generator, and he said what's the heat rate? What is it? 3412 over the efficiency. 3412 over the efficiency. Piece of cake, right? And so that number is 11,000 BTU per kilowatt hour. And we said that if you go above 10,000, people basically in an actual power plant, they was like, this is horrible, we don't wanna do 10,000, we wanna get lower. Why? Because their BTU is what they pay to the natural gas company, and the kilowatt hour is what they earn from customers, right? So they want this number to go down so that they don't have to pay too much, and they increase their margin of profit. Okay, so here's a more comprehensive example where he give you all the parameters through the plant, the compressor, the combustor, the turbine, and he will ask you to determine the overall thermal efficiency and the heat rate, and sketch the TS diagram. And is it the fuel flow rate? What? Is the fuel flow rate small compared with the fuel air flow rate? Yes, of course it will be. How we get this? The mass fuel over mass air, right? So the CB delta T divided by the heating value will end up showing you that equation that we used in the previous example, right? So this is just like the example that we had before, and he's doing it together again for those numbers. He's solving the compressor and the turbine and getting eta thermal, and he's using those CP, C prime, C double prime for the compressor, the turbine, and the combustion chamber, right? And eventually he's getting the heat rate. So, and the fuel air ratio 0.017. So those are the equation that we have for the gas turbine. So if we want to do a little bit more accurate job in the turbine, maybe we shouldn't make it look at, I mean, when you look to this, what is wrong with this equation for eta thermal? There is no m dot, there is no m dot, but he cancelled them, right? Why he cancelled them? Because he think they are all the same. M dot in the compressor is the same as m dot in the turbine, is the same as the m dot in the combustion chamber. So that's why he cancelled them, and that's why you don't see m dot in any one of those three terms. So what happened over here is that he said, wait a minute, the turbine have different m dot air plus m dot fuel. How high? Again 2%. So you can basically just say this is m dot air multiplied by 1.02, but that make it a little bit more accurate, right? And the same thing for the combustion chamber. The flow leaving the combustion chamber is a little bit bigger than the flow entering, right? So he's trying to improve a little bit, but this is not also that accurate, because flow coming in is m dot air multiplied by CP T3, and the flow leaving is m dot air m dot fuel T4, right? So here he's showing that the actual process will end up being not isentropic, and then in the combustion chamber, when we assume it's the same pressure, there will be a little bit pressure drop, and then here is the expansion in the turbine. So this is plotting it on a TS diagram, plotting the actual cycle on the TS diagram, and you see how a little bit different it is from the Brayton, the air standard Brayton cycle, which was like vertical, constant pressure, vertical downward, right? Very good. So here he is trying to make it a little bit more accurate, right? You can see how he's adjusting m dot air at the compressor, he's adjusting the m dot at the turbine, and he's adjusting also the m dot in the combustion chamber. And this look a little bit more complicated, but this is nothing but let's divide everything over m dot air. So you get here 1, you get here 1 plus what? Plus fuel to air ratio. And here if you divide this term over m dot air, you get 1 plus fuel to air ratio, and you get that expression. So this is the eta thermal that get a little bit more accurate, because he's accounting for the m dot of the fuel. So in previous exams I would specifically tell them calculate the thermal efficiency neglecting the m dot fuel. So they will use what? If I said neglect the fuel mass flow rate, they will just use this expression, and then I will tell them calculate it again taking into account the fuel mass flow rate. Then you would use this expression, right? Or this, they are equivalent, right? Very good. So next he will show us different version of the gas turbine cycle. So all those modifications are trying to improve the efficiency. So this guy, this is a heat exchanger, they call it a regenerator. What is that exactly doing? So if you have a gas turbine, I'm plotting the TS diagram, and it's like this. And this will be really useful for gas turbine that's not running by natural gas combustion, but running by a nuclear reactor. So there is, remember, there is in the previous homework there was gas cooled nuclear reactor. So they send helium, and the helium went into the reactor, cooled the reactor, and then he took it back to expand in a turbine. So what happened is the reactor will take that helium or whatever the gas is and make it very hot. And so when you expand in the turbine, look at this, the exhaust of the turbine is very high compared to the exit of the compressor. So what in normal situation, what will happen? You will take this guy leaving the compressor and you will send him into your combustion chamber or reactor or whatever your heat source is, and you get heated basically all the way from 1 to 2. And so in that modification, he would realize that if I'm leaving the turbine at 3 and it's pretty hot, why wouldn't I cool the turbine by heating the gas? So then what? Then you are saving the fuel. The fuel will just have to heat this part, and this part is done for free because anyway I was gonna cool my gas before I send it back again to the compressor. So that is the point behind this regeneration cycle. And this should remind you of the, if you remember the Rankine cycle from Thermo 1, you probably had it in the last chapter of Thermo 1. They had a regeneration cycle or regeneration modification to cycle, where they will take a little bit of the hot steam from the turbine and they will heat the water before it go to the boiler, right? To help the boiler in its job. So that's exactly what's happening over here. Compressor finish, the pressure is high. Before you send it to the combustion chamber, you take the exhaust of the turbine and you use it to heat the inlet to the combustion chamber, right? The second modification is using intercooler in the compressor. So why we are doing this? So you will be surprised to know, or maybe you already know this, isentropic compression is not really the best compression. Okay, you think everything isentropic is perfect and we cannot get anything better than this, but no, isentropic compression is not the best compression. The best compression is, what do you think? The best compression, if this compressor is like the dream compressor, he will actually do it isothermally. Okay, he will go, this would be 2 isothermal. Okay, so we'll call it 2D2. Okay, so D temperature or isothermal. So if you go around this route, this would be the least work. Okay, and if you think, if I ask you how much is this work, don't tell me what would be the wrong answer. If I said what is the work of this isothermal compressor, you will be tempted to think it's 0, right? Well, it's CB T2 thermal minus T1, which they are the same, therefore it's 0. Wrong. I know that we said before that the isentropic compression was 1. Before we said what? Work compressor was CP T2 minus T1, right? T2S minus T1. And even if it's like this, and this is 2, that work also was CP T2 minus T1. Why did we say this? Because this was isentropic and this was adiabatic. In both scenarios there was no heat transfer. And so how do we calculate all those expressions? Where does this come from? The work. It always come from the one and only Q dot minus W dot equal M dot delta H. Okay? It always come from the energy equation, the first law of thermodynamics. So in case you are isentropic or adiabatic, there is no Q, and therefore the work become M dot H. And assuming constant Cp, then the M dot delta H is become Cp delta T, and you can basically say here is the work and here is the actual work, and it's like you can really measure the distance and say that is the work because it's Cp delta T. But in case isothermal work, not adiabatic or isentropic, isothermal, the work will not be this. So how do I get the work then? And why this is not working? Shouldn't I apply the first law? Of course you should apply the first law. First law is always correct. Q dot minus W dot equal M dot delta H. That is correct. So what's the problem then? Anyone for a free quiz? It's this guy. I cancel it before because adiabatic or isentropic or adiabatic. Isentropic or adiabatic. Here is isentropic and here is adiabatic. Both of them has Q dot 0. But if I go isothermal, will Q dot be 0? No, it will not. How do I actually go isothermal? How do I compress the gas in isothermal fashion? I will have to always remove the heat. He wanna get hot as you compress him. But if I am fast with my heat transfer, always cooling, I will be able to go isothermally. Okay? So this is very hard to do, and one company a few years ago, they managed to patent a method to get isothermal compression, and they raised millions of dollars from investors that actually spend money on them so that they make an so what's the application of their compressor? Why did they want it to have very efficient compression process? They wanted to build it as an energy storage facility. Okay, so they wanted to basically find a way to use wind energy or whatever the source of energy. If you have mechanical energy basically and you don't want to use it right now, customers are not using it. They figure they can store this as compressed air, and then they can use the compressed air later to run a turbine when the customer need the extra work. And so a trick to their invention basically is to do the compression very efficiently so that we don't lose energy storing the air at high pressure. We want to do this as smooth as possible, and they managed to do it isothermally. So how do we do it isothermally? We have to cool, I guess, very slow, not cool very slowly. We have to compress very slowly so that the cooling can catch up, and you need a very efficient cooling. Okay, and so they managed to cool it by spraying water and letting the water basically absorb the heat. Therefore, the air will get cooled very quickly. Right? So, and then the water will get a little bit hot, but then they figure, well, we can use the hot water later on, extract the energy from it. So the point is then isothermal compression is the way to go, and sometimes you cannot really go that slowly. You don't have all the time in the world to compress very slowly and keep cooling. So but still you really would like to do isothermal. You want to go from this P1 to P2 isothermally, or as isothermal as you can get. So what do? Rather than going up like this, they will go up midway, and then when they are here, reach that pressure, they send the air to a heat exchanger. And that heat exchanger will cool the air ideally to what? To T ambient. You cannot get lower than T ambient because you are cooling with, correct, T ambient. And so once you are here, you go up again. So believe it or not, this 1 to A to B to 2, this 2 steps require less work than going from here to here. So what I'm saying is that 2 isentropic work and constant pressure heat rejection, this cooling, we are assuming it's constant pressure heat rejection. Of course there is pressure drop in the pipe, that is basically you are sending the flow through. It's an intercooler basically, but the point is that work if you add this guy, I need to change the color. So if you add this and this, you will realize that it is less work than this. Okay, it's as if really the lines are getting closer together, and so doing this, it's much better to actually doing this and then doing this. Okay, it will save you work. So what is the catch then? Why everyone should do this then? That's so cool. Well, the catch is the heat exchanger. You need to build that intercooler, right? You need to build intercooler. And so if I just Google here intercooler air compressor, so it takes a heat exchanger, right? And so that's added cost and added space, but it does help the compressor work to get smaller by having an intercooler added to it. Alright, very good. So he finished by showing us an example of gas turbine already in service, and you can see the best one of them can drop their heat rate, can drop to what, 8,000 9,000 BTU per kilowatt hour. So those are impressive, right? When the heat rate drop that low. When they are big, that's horrible, right? When they are getting really small, they become comparable to a steam power plant. And so he finished the chapter by more example of heat, basically gas turbine that's already in the surface. So now there is this simple cycle and there is a combined cycle, and we will see what is a combined cycle in a minute. Here's the pictures. So the difference between the gas turbine that used for power and the gas turbine that used on airplanes is the weight. So the one, of course, on airplane has to be very light. Okay, and look at this. Here's the first stage, low pressure, and then to intercooler, and then he come back from the intercooler cold enough so that he can go to the high pressure compressor. Alright, so now what is the combined cycle? So combined cycle is really the way to build power plant right now. So most of the new power plant are always built as a combined cycle. So here is the gas turbine cycle, right? And he's trying to make it real cycle. So you can see he's not going up isentropically, he go up a little bit to the right. Then he had the combustion chamber, and then when he go down, he does not go straight down, but he go out down a little bit to the right. And he has intercooler regenerator in the middle, right? Regenerator cycle. He's using the exhaust of the turbine to heat the inlet to the combustion chamber, and that combustion chamber can be from a nuclear reactor, can be from just like combustion chamber that's being using natural gas, doesn't really matter. The point is the 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 exhaust of the turbine, huh? If the exhaust of the turbine is still, after all this, is still too hot and you don't want to throw it away, what do you do with it? You send it into a steam power plant, right? So you basically tell yourself, I don't want to throw away that very hot exhaust, even here at 6. I don't want to throw away that hot gases in my stack. So what do? You use this to boil the steam in a Rankine cycle. Okay? And so a steam cycle by itself cannot peak more than what, 40 something, 45%? That's a steam cycle by itself. But when you put a gas turbine and you use the exhaust of the gas turbine to run the steam power plant, your efficiency go up to like 65% or something. So the power plant in Owasso over here in Oklahoma have an efficiency of 65%, but the one in Jenks have an efficiency of 40%, more or less. So what is the difference? Because the one in Owasso is running a combined cycle, and the one in Jenks is basically just a steam power plant, and their gas turbine are not coupled to the steam power plant because the steam power plant was built first, and the gas turbine, they just put them and they just install them as a peaker for load, right? So we'll talk more about the combined cycle next time. But it's basically would look like this. So here is your gas turbine, and the exhaust, rather than being sent to the stack into the air, no, you send the exhaust into the boiler of the steam power plant. This is the steam power plant, and this is the gas turbine power plant. Right? So you will be very proud to know that the first place in the whole world anyone came up with this idea, the idea that increase the efficiency of steam power plant from 40% to 65% all over the world. That's the way people build power plants right now. The first place that if this ever was done was in Oklahoma. Okay, they figured, well, we have a hot gas exhaust coming from the gas turbine, why should we throw it away? And they basically said, let's actually generate some steam with it. And that was the first time this idea was born. Okay, so we will I'll finish here, and we will study this combined cycle where a gas turbine run a steam power plant. Sometimes the exhaust of the steam power plant can completely drive, the exhaust of the gas turbine can completely alone by itself drive the boiler of the steam cycle, but sometimes you need a little bit more fuel to burn. So auxiliary firing, so the exhaust is pretty hot, but you know it needs a little bit more to do all the boiling that the steam power plant will do. So I'll finish here for now.